we think that this experiment is a great next logical TRL demo. And for those of you who have heard our presentations and discussions, we like to throw a lot of information and data on the screen and for you to have going forward. So we have, you know, these habitable biospheres in the inner disk, and there are a lot of similarities between both Venus and Earth. And I wanted to highlight a few here, that being the sunlight with around 100% more wattage per square meter in the cloud layer compared to the surface, and then there's also a shorter transit time of around 4 months, and so billions of years ago, Venus, you know, had this vast ocean until something happened, 500 million to a billion years ago, and remember reading about this theory, and that was proposed that Jupiter came in, you know, during the Grand Migration and really stripped the magnetic field from Venus and Mars, we believe, and then gradually over time induce and build this runaway greenhouse effect until what we have with Venus and Mars in the present day. And to really put on our critical thinking caps in terms of, you know, how else this Grand Migration influenced other celestial bodies and other star systems too. So here's a slide on the zonal winds in the Venus atmosphere as a function of habitability, and so you know, one of the, I think the near-term dragons, to say, of Venus would be the high wind speeds, you know, around 300 to 400 kilometers per hour in the cloud layer, and so these clouds are in constant motion, and these speeds, they complete a circle around the planet every 4 days, and so here we can see a plot of the latitude of Venus versus the zonal wind speed, and we can see here that we've highlighted in green around 60 degrees latitude north and around 60 to 85 or something south, that the wind speed is actually significantly reduced, and such that we have around 100 to 200% less wind. So this data was measured and collected by the Galileo flyby in 1990, over 30 years ago, and so this corresponds to 20 to 40 meters per second with a 40 to 78 knots. And so this other study found that the fastest wind speeds with the altitude is around 65 to 72 kilometers, and that some of the wind speeds peak around 40 to 50 degrees south, which is observed here in the data. And here's a chart on the upper cloud layer, and specifically around 70 kilometers in altitude, where we have this upper haze. And so these cloud layers primarily consist of the sulfuric acid, and but then also water, and so these reduced wind speeds, I believe the systems and habitats would circle around over 8 days or so around the planet with this reduced wind speed, which introduces and influences the thermal operating window for systems. And so we have here's a chart on the nighttime on Venus with the altitude, and we can see here it gets to around -43 degrees C, around the top of the upper cloud layer. And so trying to understand, really what are the effects of turbulence on habitability, and so it's awesome to see NASA pioneering, NASA and researchers pioneering the LEAVES mission, with plan to launch MEMS probes around 120 grams each, the 1 meter drag array and error brake dropped off from 145 kilometers, with the intentions and purpose to really measure the small scale waves in turbulence and the magnitude and direction of the vertical motion, and the convection. And so let me start asking, well, start off, what is turbulence? Well, turbulence happens when there's, a fast and slow wind speed that are stacked close together, and so this creates this vortex that creates pockets of air and rises or drops systems, and so that turbulence can range from light to severe, from 1 to 30 meters, and it's really like, how comfortable are we with a butterfly effect, and really, how many butterflies are we going to be feeling? So here we've outlined some research questions, and to really help understand the wind speed, and could anti-collision recognition lights and other sensors be utilized for docking, and then what novel designs could help absorb the turbulent shock? And here's a great study and experiment where they measured the turbulence with a tethered anemometer on a balloon above Antarctica back in 2016, and they measured 3D wind vectors, and they use this instrument, and so these things called radiosones can also measure the pressure, temperature, and relative humidity, and with antennas to calculate wind speed and direction. And we can also use the micro aerial vehicles and aviation sensors and inertial measurement units, but also quadrotors and a lot of other systems, accelerometers to collect all sorts of data relevant to the turbulence of the systems. And here's a slide on the Reynolds numbers, and to really help us model the turbulence and mathematically derive equations for how our systems are going to be operating and experiencing. And so the Reynolds number can determine if the flow is laminar, transient, or turbulent. And when you have a Reynolds number above 2300, you have turbulence. And this can be calculated from this equation here. And then here's the Rayleigh number as well, to help us quantify the Rayleigh number in terms of the fluids and viscosity, and how turbulence relates to momentum and heat flux as well with these equations. And so here's a slide on the really figuring out the water cycle and the abundance and collecting water in the Venetian atmosphere. And so they measured around 34 parts per million in Venus from the study in 2014, and then a lot of other data suggests, but this was lower, around 30 to 45 kilometers, and so a lot of data also suggests around 20 parts per million of water, which corresponds to 3.93 times 10 to the 15th kilograms of water, which is 0.002% of water vapor in the Venetian atmosphere, primarily located mostly within the cloud layer here, 48 to 66 kilometers in altitude. And so if we calculate the volumetric difference here, we can see that I believe there's over 83.638 million kilograms of H2O per cubic kilometer and And so it's quite interesting. We can use these spectrometers to collect more detailed water measurements, and that we also learned that this H2SO4 is actually created from the water vapor, and from this reaction here, O2 plus SO2 plus H2O. And so we should be able to easily filter out the water from the sulfuric acid and collect a lot of water to support life in the clouds, and can do this through this filtration process similar to the WAVAR and zeolite beds, and these hydrophilic crystalline aluminosilicate materials, and so that these researchers they design the system and use pumps that operate thermally and adsorb the CO2 at night when cold, and then desorb the H2O from the zeolite. And so the large air volume and the desorption time are probably the energetic cost. And so here's some research questions. How much more H2O is in the lower layer, and is water co-located with a sulfuric acid? And also, what's the mean free path of H2O? And is it parallel, diagonal, and also what molecules could we potentially mitigate this formation? Yes. And so coming back to the topic here and the presentation of this ISRU flight demo and this in-situ air production in the Venetian clouds, we're proposing to design, build, and test a sub 20 kilogram payload in a Venetian environment with this outline and diagram here, with a balloon fluoropolymer and mylar inner layer, and the small 20 kilogram payload underneath with this ISAP unit with an inlet, swirl pump, and solid oxide fuel cell. And also we think an inflation system to help pump a habitable environment, 21% oxygen, 78% nitrogen as lifting gas into the balloon here. And so another research goal is to really also help quantify the turbulence. And so I think a lot of the demos will help quantify the turbulence. And so we think that it's this could operate for around 60 days or less, and I think it makes sense to lean more toward the top of the upper cloud layer, around 68 to 72 kilometers in altitude, with these reduced wind speeds, and at these latitudes, 60 in the 60s, and so hopefully such a demo would help advance the design and test with a larger multi-kilowatt in-situ air production unit to support organisms and humans in clouds. And we're thinking that it's similar to MOXIE, and we think that there are a lot of similarities in the design of the solid oxide fuel cell, and so here's a slide on how MOXIE is designed and developed in the subsystems and the chemical reactions here. Power. Yes. But the difference being that we have this a differential outlet pressure and inlet pressure, which will influence the compressor design. And so here we can see the compressor and the solid oxide fuel cell. And really slide here on helping quantify the scroll pump compressors. And so Air Squared developed this scroll compressor for MOXIE and the Mars 2020 Perseverance rover. Yes. And so they bring over 30 years of experience, and that these scroll compressors would operate at less of a higher pressure ratio. And then here's some specs on the compressor system that was proposed with this around 2 kilogram mass for the fuel cell. And so we think this is another relevant system with the vacuum pressure swing adsorption systems to separate the gases and purify the gases with these zeolite beds. And so, with a similar compressor, we could, filter out the carbon dioxide and pass them to the fuel cell, and then instead of we can adsorb the nitrogen or pass it through, or release the nitrogen after the absorption in the bed and then exhaust as a waste gas. So there are a lot of systems and designs, and with 4 steps being adsorption, depressurization, purge, and off-gassing. So here's another slide here, kind of looking at the bigger picture, and but before then, coming back here in terms of we're still kind of exploring how such a design would integrate into the payload design, and after the scroll pump and somewhere in here. Here's a slide on the technology readiness level demo roadmap in the 2020s toward supporting humans and organisms in the clouds of Venus, and so really quantifying the turbulence layers, the air production and airlock and entry to help ascend in above the payload into the balloon and the atmosphere of the cabin, and then some other demos on really tether docking and how to gain more steerability and maneuverability in the clouds, and then also potentially transmit electricity to nearby habitats and potentially mass as well, horizontally and vertically, and also how to really enable these kinds of enable what the beautiful artwork and sci-fi have outlined, and so we're starting to think more about how payloads and humans could enter into such a habitable, breathable atmosphere inside the balloon, and about what the subsystems architecture would look like with the tethering, and so we think that some solutions are to really these near real-time imaging processing and algorithms for the docking and tethering, and we think that a lot of the ISRU systems on Mars might also be relevant and applied, and such as the CO2 breathing electric propulsion systems, and some other designs. And really curious too on these the shock absorbing turbulence systems, and how that could help absorb some of the turbulence, and then the various electromagnetic, polar, chemical attractions and systems that could help dock vehicles together, both in LEO and Venus. I gotta think about those ones, but thanks so much for listening, and take any questions, and yes, hopefully help, and look forward to advancing the research toward Venus and also Mars.